Okay, so we've had some practice with writing acid-base reactions and ones that occur in various steps, and we care about that because it allows us to do number crunching with titration problems. So let's see what that might look like. They're doing a titration here where, and to remind you in case you've forgotten, a titration happens when you have a solution and you know there's some chemical in it, but you don't know how much. Like you think there might be lead in your drinking water, or you think this athlete's blood might have a performance enhancing drug in it, and you want to know what the level is. And so you react that chemical with some other thing whose strength you know, and you see how much of your known chemical it takes to react with the unknown amount. And so if you have something that's, say, reacting with lead in your water, if you put in one drop and it gobbles up all the lead that's in the water, then you think, okay, well, there can't have been that much lead because it only took a little dab of this chelating agent to tie up all the lead, so the level of lead was very low. If it takes a cup and a half of chelating agent to take all the lead out, then you think, okay, this water is loaded with lead because it took a lot of chelate to remove the lead from it. And we can be more specific than that. We can actually do a calculation to determine how strong the concentration of something is. And it starts with writing a reaction for what's happening between your unknown chemical and the known one. So, what would that look like? If we have 10 milliliters of sodium sulfite. Now, we'll get to the 10 mil in a minute. For now, just pay attention to the chemicals and we'll get a reaction written. We'll take care of the rest of this in a moment. So just like in the previous examples, sodium sulfite dissolves into sodium, which we do not care about because it isn't an acid or a base. And that's reacting with hydrochloric acid. So what will the reaction between those look like? Well, sulfite ion is this, SO3 2 minus. And hydrochloric acid, once it's in water, quickly transforms into H3O. And chlorides, which we don't care about because they're a feeble base. And so these can react with the H3O giving away a hydrogen to form the hydrogen sulfite ion and water. And if we keep pouring in acid, we can get a reaction where the HSO3 picks up a second hydrogen. If you're wondering why I'm writing this second reaction because you've read the problem completely, you're right, and I'm going to address that in just a second. Hang on. Plus H2O. Okay, so there are two reactions that can happen here. One for if we put in some acid, and one for if the first reaction completes and we keep adding acid. In this case, though, they say in the titration they're only going to what they call the first endpoint, meaning they're only going to the point where this first reaction finishes and not the second one. If they said second endpoint, we'd be counting both of these, but first endpoint means goodbye second reaction, we do not need you. This is the reaction that's actually happening. SO3 plus H3O. And so that's what we're going to do our calculations from. Now they say we had 10 milliliters of sodium sulfite. So over here our volume is, they said 10 milliliters, I'm going to say 0.010 liters. And I'm going to create a little more space here because we're going to need it in just a second. They say the concentration of the hydrochloric acid was 0.225 moles per liter. Moles per liter. And the volume required at this endpoint was 14.2 milliliters. That can't be about the sulfite. They already gave us a volume for that. It's got to be the volume for the acid. So the volume over here was 14.2 mil, or 0.0142 liters. And the question is, what concentration would we have had for the sodium sulfite? Concentration equals, don't know. Now the idea is when this reaction is over, our H3O has completely reacted with our SO3, meaning the number of moles of those two things must be the same. Well, we can find a number of moles for the H3O. There should always be a number of moles somewhere that you can find, or these problems are a non-starter. So always try to find a number of moles wherever you can. In this case, n equals CV will do it for us. C is 0.225. V is 0.0142. And calculation occurs 0.0142. And I get my number of moles for the H3O is 0.003195. That's the moles of H3O. Now, the ratio for these is 1 to 1. Almost always when they say first endpoint, the ratio is going to be 1 to 1, and that's very nice. It means our number of moles for the sulfite is the exact same number as what we just found. We have equal numbers of moles of both of these chemical species. 0.003195 moles of SO3. Can we get a concentration from that? Indeed we can. Concentration is your number of moles divided by your volume. So in this case it's 0.003195 moles divided by, and our volume is 0.01 liters. So that gives 0.3195 moles per liter for the sodium sulfite. A small tweak with this one, significant digits, they gave us 3 for a couple of these data, 4 for others, so our answer should only have 3, which means instead of 3195, this should round to 0.320. All right, so you have to write a reaction, or it is strongly recommended to write a reaction. Then get a number of moles for something. If you can't get a number of moles, you really can't get going on a problem like this. Once you have moles of one substance, you can jump to moles of another substance, and from that you should be able to calculate whatever unknown thereafter. So let's do a bunch of those and see if we can do them consistently. A titration of citric acid with sodium hydroxide goes to the end of the second quantitative reaction. So you remember citric acid was the kind of complicated one, which I'm looking for right now. C3H5O. C3H5O and then 3 carboxyl groups, or carboxylic acid groups. Now, they say second quantitative reaction. What that means to us is that we're going to be adding 2 hydroxides. The first endpoint would be when one of these has given away its hydrogen. The second endpoint is when 2 of them have. And so that would mean we have C3H5O. Of these 3 carboxylic acids, one of them still has its hydrogen. The other 2 do not. And in the process, this isn't going to affect the calculation, but we're going to make 2 water doing that. And I'll try to keep my reaction correct. 2H2O. There. So that's what this looks like to the second endpoint. I could have written these 2 reactions separately and then added them up and then canceled spectators, but perhaps you'd appreciate it if I don't take too much time on that part. So second, essentially when they say second reaction or second endpoint, it means 2 hydroxides went in. Now, for information, they tell us we had 10 milliliters of citric acid, so our volume here is 0.010 liters. Volume over here, not sure yet. The concentration of sodium hydroxide was 0.123. 0.123 moles per liter. I'll try to keep my volume in one row and my concentration in another. It doesn't matter all that much, but maybe that'll help you stay organized. And they say the equivalence point values were, so they ran this titration 4 different times and got 4 different numbers. And the general rule is that we would average all of these, but before we do that, there's something else that we normally consider when we do a bunch of trials like this. And the important fact here is that when you do a titration, every so often you just screw it up and put in too much or too little chemical, and you get a number that isn't valid because it's very different from the rest of the trials. In this case, you can see we have 12, just a little under 12, just a tiny bit under 12, and substantially more than 12. This number, very different from all the others, is what we call an outlier. Not liar as in it lies to you, but as in it lies far away from the other numbers. Now, sometimes outliers are important information and they're a big deal, but in some cases, outliers just mean human error. It means a person did this 4 times and one of the times they made a bit of a mess of it. And so in chemistry, traditionally, our first reaction to an outlier like this is to throw it away. If you see a value that is way different from the others, discard it, just assume it was a mistake, and average the other 3. If you average the other 3, you get a volume of 11.95 milliliters. And that is what we're going to use for our V here. I'm going to put AVG for average equals 11.95 milliliters. Again, ignoring outliers, not always a great idea. Sometimes this is the science trying to tell you something very important and you should pay attention. But in cases where humans are liable to make mistakes, very often that's all this is. And so that's how we justify chucking it. So we have this average of 11.95 milliliters. That can't be for the citric acid. We already have its volume. It's got to be the volume for the hydroxides. 11.9, actually, sorry. It's 11.95 milliliters, but volumes are supposed to be in liters typically, so let's go with that. Okay, so that's all the information nice and organized. What do we do with it now? There's something that we should always try to find in these problems and that we're kind of stuck if we can't find it, and that would be a number of moles. We can't get a number of moles over here because we don't have C times V. We have the V but not the C. However, here we're in good shape. Start where you're stronger and where you know more stuff. We can get a number of moles here because it's N equals CV, which would be this concentration times this volume. Concentration 0.123, volume 0.01195. We get that the number of moles is 0.00146,985. Moles of OH. That's obviously way, way too many significant digits, but we'll carry them for now. Now, the amounts of hydroxide and citric acid are not identical. According to our reaction, however much hydroxide you have, in this case 2 OHs, you only have half that much citric acid in this reaction. So this number divided by 2 gives you the citric acid number. If this were 30, this would be 15. If this were 200, this would be 100. If this is 0.00146,985, we have to take that number and divide it by 2. And that tells us our number of moles of citric acid is 0. Reading off my calculator, 0.00734,925. And that's moles of, I'm just going to put Ca for citric acid because writing this thing out is annoying. Now that we have our number of moles, they're asking for the concentration of the citric acid. Well, we should be able to do that. Concentration is number of moles divided by volume. So it's that big number, moles of citric acid, divided by, and our volume is 0.01. So that gives us 0.0734925 moles per liter. And let's get our significant digits figured out here. 4, 3, 4. Okay, so our worst measurements have 3 significant digits. So this gets cut down to either 0.073, round up, 5 moles per liter, or you could say 7.35 times 10 to the minus 2 moles per liter. Okay, titration experiment, 78 mil of blah, 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 blah. Potassium hydroxide. We want to write a reaction first. So on my first reading through one of these, I'm really ignoring the numbers, and I'm just looking for what are the chemicals. Who are our characters in the story we are about to tell? Potassium hydroxide dissolves into potassium, don't care, and hydroxide. Potassium is important in a lot of ways, but not an acid base. It doesn't do anything there. And is required to react ascorbic acid, also known as vitamin C. And in my data book, that is H2C6H6O6. So it's an acid, C6H6O6. So as I read this, the C6H6O6 is the ascorbate part that is not going to change. These are the two hydrogens that could come off. And how many of them do come off? Well, they say it reacts completely, which would mean both hydrogens come off. It's not to the first endpoint. It's completely means you keep going until there's no more hydrogen that can be removed. So that would mean we're using two hydroxides. And this reaction is going to give us C6H6O6, ascorbate ion, and a couple of waters. You've probably noticed from the other examples, the right side of these reactions ends up not mattering, and the part we really care about is the ratio here, which is 2 to 1. Also, having these reactions down gives us a nice way to organize our information. We can put all our OH information right under the OH. We can put all our ascorbic acid stuff right under the ascorbic acid. So, what have they told us? 78 mil of 0.5 mole per liter solution of, okay, all this is about the hydroxide, so 78 mils, 0.078 liters, and concentration 0.5 moles per liter. And for the ascorbic acid, we have 50 milliliters. And concentration, don't know. All right, where do we start? Moles, must have moles. We can get a number of moles for the hydroxide because we know volume and concentration. We can say N equals CV equals, there's our C, there's our V, we get 0.039 moles of hydroxide. So how much ascorbic acid do we have? Is it this? Hope you said no. The ratio here is 2 to 1, meaning the hydroxide amount is twice as great as the ascorbic acid amount. So if you want the number of moles of ascorbic acid, you take this number and cut it in half. So our number of moles over here is 0.0195 moles. And now that we have that, we can find a concentration. Concentration is moles per liter because you find it by doing moles divided by liters. 0.0195 divided by, and our volume is 0.05 liters. Concentration 0.39 moles per liter. Now, let me check if 3 sig digs, 3 sig digs, 3 sig digs. So, sorry. My calculator gave me precisely 0.39, but we have to give that to 3 significant digits. So, okay, we can pad it out with a 0. There we are. Okay, 100 milliliters of Sodium carbonate. Standard solution is prepared with sodium carbonate solid, fine. And the standard solution then reacts with hydrochloric acid. So our reaction is between, we don't care about the sodium, carbonates, reacting with HCl for our purposes is, you could write the reaction with HCl, but H3O is what's really happening. And is that going to second endpoint? There could be two reactions here, and they say it reacts completely, which would mean two hydrogens, enough to completely fill this up and turn it into carbonic acid. And we'll get two water from that. So this base turns into its conjugate acid, two steps up. These acids turn into their conjugate base, which is water, twice. Okay, and what else have they given us? We have 10 milliliters of the sodium carbonate solution. They call it a standard solution, which just means one where you know the concentration. So we have 10 ml of the carbonate solution. "30 milliliters of the acid. And we need a concentration, and they said we had one for the carbonic acid, but we kind of don't, except that we do. They've given us its mass. They said they started with 3.5 grams of sodium carbonate solid, so we have to do a little side trip here, unfortunately. We could get our concentration because it's number of moles divided by volume, and we can get a number of moles because it's mass divided by molar mass. So, mass, 3.5 grams. Molar mass, it's sodium carbonate, which is Na2CO3. So, 22.99 for sodium, double that. Carbon, 1201. 3 oxygens is 48. I get 105.99 grams per mole for the molar mass. So that goes here. So 3.5 divided by 105.99 gets us a number of moles. 0. What are we going to have for sig digs here? 3, 3. The answer is going to have 3 significant digits, so probably carrying 4 is probably good enough. 5 would definitely be good enough. 0.033022. There. Okay, that's our number of moles. We care about that because we need it to get a concentration. So now that we have this number, we can start winning up here. 0.33022 divided by, and our volume was 0. Trap. They said they put this 3.5 grams of sodium carbonate in 100 mils originally. They didn't use all of it. They only used 10, but the mix was with 100. That's the number we must use here. So 0.33022 moles per liter. That's our concentration for the carbonate. Now that we have that number, I'll just copy that up here. 0.33022 moles per liter. And I'm going to clear this out. We need the space. Okay, so now finally this looks like the other problems, where they used to just give us the concentration. This time they made us dig for it, but now that we have it, what's our next step? Find moles. Always find moles. Number of moles here is N equals CV. If you're thinking we already know the moles, that was for this entire container of solution because they made a big batch. They made 100 mils of it, but then they only took a tiny bit to actually use in the titration. So this is the number of moles that are actually in the titration that we're finding here. C is 0.33022. The volume is that. So we get 0.00333022 moles of carbonate. So how many moles of acid would that mean? Do the numbers match? Nope, they don't, because these coefficients are different. This says however much carbonate you have, there must be twice that much acid. So if this is our amount of carbonate, double that, and you get 0.00666044. That's our moles of acid. And now that we know that, we can get a concentration. Concentration is N over V, 0.0066044 divided by, and our volume is 0.03. 0.00666044 divided by 0.03, and I get 0. How many sig digs are we looking at again? 3? Yeah. 3 sig digs, so 0.220 moles per liter. Aye, 2 more. Okay. 50 mils of HCl solution is required to neutralize sodium hydroxide. Okay, so this is a 2-step. Okay, this is about as mean as titrations can get. This is 2 titrations, one after the other. They start out by saying that they titrate HCl with sodium hydroxide. So please ignore all this for now. We're just going to work with that first line for the moment. They say we have HCl, strong acid, reacting with sodium hydroxide, and that'll produce a couple of waters. It's the left side I care about. What I care about on the left side is that this reaction is 1-to-1. 1 HCl will neutralize 1 sodium hydroxide. They say that we had 50 ml of the acid solution, 0.05 liters. The concentration was 0.25 moles per liter. And we had 100 ml of the hydroxide. So we can get a number of moles over here, 0.0125. Because this is 1-to-1, the number of moles of hydroxide must be exactly the same.
The cost and amortized cost is used for dead instruments.
And now we can get a concentration for the hydroxide. Its concentration is the number of moles divided by the volume, 0.125 moles per liter. Okay, so all that to say the concentration of this hydroxide solution they're discussing is 0.125 moles per liter. Now that we have that, let's reveal the rest of the problem. And we'll forget about this first part because we already dealt with that. So now they're saying, after this first titration, yeah, we're done with that. Don't want to think about it anymore. This sodium hydroxide solution, which we know has a concentration of 0.125, I'll write that in here. We're going to need that.
Okay. So, like you said, the question's going to tell you.
0.125 moles per liter. The whole point of that was to tell us how strong the sodium hydroxide was, but to make us work for it. So we have that number. Now they're saying we use this to titrate a solution of phosphoric acid to the second endpoint. And now we get a whole bunch of numbers. So
Okay.
the main problem is phosphoric acid is titrated with sodium hydroxide. Pretend you're starting fresh. So we have phosphoric acid, H3PO4. We're adding hydroxides to it. Now we could add up to 3 hydroxides and knock this all the way down to phosphate, but they say they only do it to the second endpoint, which means we're adding 2 hydroxides. This gives up 2 hydrogens. It ends up here, and that should produce 2 waters.
Well, she told her about the things that are true, anxiety and
Okay, so
benevolence.
really, if you're super great at these, you could just say second endpoint means 2 to 1, and you might not need to write out the reaction. But like I say, I always do it because it gives us a place to put all our other information. They say the volume of the acid sample was consistently 10 milliliters, so 0.010 liters there. The volume of our base, well, we have 24.5, 24.4, 24.6, and then this thing, which is way different from the others. I declare this an outlier, and I think it was probably a mistake. We will exclude that one. Averaging the other three gives us 24.5 milliliters. 0.0245 liters. Okay, concentrations. Well, we have one of them. We know the sodium hydroxide, and a good thing, too. We'd be stuck if we didn't. 0.125 moles per liter. With that, we have enough to get a number of moles. And we know we're usually off and running once we have that. Concentration, 0.125 times volume, 0.0245. Number of moles is 0.00300625. Now that we have that, what's our number of moles for the acid? It's not 0.00300625. The ratio of these is 2 to 1, meaning however much hydroxide you have, divide by 2, and that'll tell you the amount of acid. So take this number and divide it by 2, 0.00153125. 153,125. Double checking. Yeah, it looks good. So that's our moles of acid. Why do we care about that? Because their question is, what's the concentration of the phosphoric acid? Well, you can always find a concentration if you know number of moles and volume. We have our number of moles. Our volume is 0.01. So I get a concentration of 0.153125 moles per liter. And how are we on significant digits? 3, 3, 3. Yeah, this one's consistently 3 sigdigs, so our answer should be 3 sigdigs, so 0.153 ought to do it. 0.153 moles per liter. Okay. This is a single titration again, I believe. We have something with oxalic acid in it. This is often used in bleach. The bleach name Clorox is called that because it contains some chlorine compound and oxalic acid. And it's titrated until complete neutralization with potassium hydroxide. So oxalic acid is huku. And it reacts with potassium hydroxide. We don't care about the potassium, just the hydroxide part. Now, this can react twice because there are 2 hydrogens that oxalic acid could give up, and they do say complete neutralization, which means, yeah, they did titrated twice, or they did complete both reactions. This oxalic acid will get stripped all the way down to oxalate ion, and two waters will pop off it. But the part we really care about is the 2OH, that the ratio of these things is 2 to 1. You know that's going to come up when we're finding our numbers of moles. So, what do we know here? 25 milliliters of oxalic acid. They consistently use 25, 0.025 liters. And what else have they given us? The hydroxide concentration is 0.485. That's good stuff. 0.485 moles per liter. And, well, there must be something else. These volumes tell you the original and final readings on a container of potassium hydroxide as they do the titration. So when you do a titration like this, you have a long, skinny container called a burette, and it's marked like 0 up here, and then down here it'll say 10, and here it'll say 20. And you fill it up so that at first it's completely full of titrant, the chemical that you're going to add. And you read the number before you start, and then you read the number at the end. And by subtracting those, you can find how much liquid did I just use up doing this titration run. So they're saying for the first run, we started at 1.4 and we went until the burette read 17.1. If you subtract those, you get 15.7 milliliters. So that's how much they used doing the first run. Subtract these and you get 15.6. Subtract these and you get 16.0. And then here the numbers change, which apparently means the burette was getting empty, so they refilled it. They topped it off until it was up here at 0.4, and then they ran it again until they got to 16, which is a difference of 15.6. So what do you think of those numbers? Are they all in a nice cluster? Are there any that stand out? I would say this stands out. We have 15.7, 15.6, 15.6 again, and then the 16.0 makes me think they blew that one. They weren't paying attention, or their hand slipped, or they misjudged the color that they were using to identify the end of the reaction. I think 16 is too high and we should chuck it, and we should keep the other three. If we keep the other three and average them, as in add these up and divide by 3, we get 15.666666 for our volume. And so that's the number we use. The volume of our hydroxide is 15.6 repeating milliliters, or 0.015666 liters. Okay, so whenever you get a table like this is just a complicated and realistic. We're not just doing it to be mean. This really is how titrations work. It's a way of giving you the volume where you have to figure it out based on averaging a number of runs. Because when people do these, they don't nail the same number every single time. You do get little differences, and averaging those gives you a number that's pretty close to the truth. So now that we have this, we always want a number of moles. We're really stuck without that. So we can get a number of moles here by doing N equals CV. Our concentration is 0.485. Our volume is 0.01566. That's me putting in a lot of sixes. And that gives us a number of moles that is 0.007598 and then some threes. So that's our moles of hydroxide. How many moles of acid? It's not this, but it's related to this. You have to take the OH number and divide by 2 to get the amount of acid, right? 2 to 1 ratio. This number is 2 times too big. Divide it by 2 and it'll be just right. So our moles of acid come out to 0.003799 167. I'll keep the whole thing. So that's our moles of acid. And they said calculate the concentration of the acid. That's pretty often what we're finding. Concentration is number of moles, which we already have in the calculator, divided by our volume, which is 0.025. I get a concentration of 0.1519 long string of sixes. And now that we're at the end, how are we doing for sig digs? 3, 3, 3. Should be 3 sig digs, so 0.152. 0.152 moles per liter. Now, real quick, if you're looking at these numbers and saying, wait, those are two significant digits, the rules are different when you're adding and subtracting. If you're subtracting two numbers like this, then you actually, instead of counting significant digits, you count decimal places. So when you're looking at one of these, you say, this is to the nearest tenth, this is to the nearest tenth. That means my finished number, my answer should be to the nearest tenth, and it is. So when you're subtracting, you say, like 1 decimal place, 1 decimal place, my answer can have 1 decimal place. And that's true for all of these. So all of these answers are correctly to 1 decimal place. When we average them, we get an average that has, now we're switching back to significant digits because averaging is about dividing. 3 significant digits for our answer. I carried more than that. And all the other values that we multiplied and divided contain 3 significant digits, so that's why we get 3 in our answer. So sorry if that feels like a rule change. It is a rule change. It only comes up when we're adding and subtracting. 90-ish% of chemistry is multiplying and dividing, and so we're normally in sig-dig mode. But when you add or subtract, you stop counting significant digits and you count decimal places instead. So, not cheating, I promise.